Hello, I am Okoshi, Project Officer of Spring GX. Today, I'm presenting a lecture at the Green Future meeting for the first time in 3 years. From this year on, a total of 1,154 students will participate in the program. We will have to wait until the fall enrollment to welcome all of the students, but since most students have joined as of now, I would like to take this opportunity to introduce myself and my lab's research. I believe that the GX office has announced our diverse overseas study programs, including the Overseas Dispatch Program, and I would like to encourage you to apply to them and go abroad proactively. The title of today's lecture is, as shown here, Development of Green Materials Based on Physical Chemistry. I've added a subtitle, Curiosity, Basics, Encounters, and Social Contribution. In the course of running this program, I've been asked many times by participants about the relationship between basic research and applied research, and I've occasionally thought about this relationship myself. So today, taking this question into consideration, I'm delivering a lecture at the Green Future meeting. I believe today we also have second-year and third-year doctoral students who have newly joined us via additional recruitment. The Spring Project is operated with a strong emphasis on the vision of the project officer. I myself was originally a basic science researcher, started expanding to applied research, and now make some positive contributions to society. In this process, I've met various professionals and my research has expanded through industry-academia collaboration, overseas joint research, and other experiences. Today, I would like to talk about the stream of my research. Here, I would like to explain why I am serving as the project officer for this program. First, when I was the vice dean of the School of Science, where I am currently working as dean, I created numerous educational programs, such as the Overseas Study Program and the International Students Acceptance Program. Currently, approximately 100 students who major in the sciences are participating in international research exchanges. As such, I have created various programs for students, and these programs have been reproduced at the GX office and are now available to the project students. I have also proposed and realized the double degree program that is currently available to students. I personally find this program wonderful, with several ongoing collaborations, including ones between the University of Paris-Saclay and the University of Tokyo, and between the University of Manchester and the University of Tokyo. Participants in this program can obtain doctoral degrees from both overseas universities and the University of Tokyo, receiving guidance from excellent supervisors from such overseas institutions. When it comes to my past international research collaborations, I've collaborated with 45 laboratories in 13 countries. I've also promoted industry-academia collaborations, which I will describe later. With such a background, and in response to requests for a program for young doctoral students that opens a new future for them, I am now serving as project officer for Spring GX. I'll talk about the detail of my research later, but basically my research is focused on creating novel phase transition materials. I will talk about this later, so I will not go into the detail now. I also run an international research laboratory at CNRS in France and operate a project called the Heat Storage Materials Lab at the University of Tokyo. In my lab, I have worked as a professor since 2006. This is my lab. Some of you might have seen it on the Hongo campus. It is the oldest building on the Hongo campus. We conduct our research in this building. The first professor of our laboratory, which was named the first course of chemistry at that time, more than 100 years ago, was Professor Kikunae Ikeda. Professor Ikeda is said to be the pioneer of physical chemistry in Japan. Professor Ikeda went to Germany as a government-sponsored researcher and joined a laboratory headed by Professor Wilhelm Ostwald, a German Nobel Prize winner in chemistry. Professor Ikeda learned physical chemistry there and brought it back to Japan, which is why he is said to be the father of physical chemistry in Japan. Professor Ikeda's most well-known achievement was the discovery of umami, which was monosodium glutamate extracted from 38 kilograms of boiled kelp. He named it umami, which is the current umami seasoning. Professor Ikeda, the professor 6 terms ago in my lab, there may be some missing information here, but Professor Ikeda granted a license for manufacturing the umami seasoning to Suzuki Pharmacy, which was run by Mr. Saborosuke Suzuki. It is amazing that Professor Ikeda, immediately after conducting the research on umami, filed a patent for it. The patent was granted within 3 months. He then provided the patent to Mr. Suzuki from Suzuki Pharmacy. The Suzuki Pharmacy is the current Ajinomoto company. Today, we know that umami receptors are located on the tongue, but this was first discovered after the year 2000. This means that Professor Ikeda had made a prominent discovery 100 years ago. At the same time, on his way back from Germany to Japan, Professor Ikeda visited and stayed in London, where he shared a room of a dormitory, or maybe a hotel, with Sosuke Natsume, a famous novelist in Japan. It is said that they conversed every day and night throughout an entire month. In his personal record, Mr. Natsume wrote that Professor Ikeda was a man of great wisdom and interest in many things. He is also a man of great insight and fine character. It is said that Sosuke Natsume had been relatively emotional in his writings until then, but he came to write very rationally after he met Professor Ikeda, a man of rationalism. Mr. Natsume himself said that he was very much influenced by Mr. Ikeda, and later wrote, "I am a cat," and "Sanshiro." In such a way, I think it works quite effectively when individuals with completely different backgrounds, namely science and literature, meet and talk with each other to influence each other. Actually, Professor Ikeda discovered the umami component after such an experience, so I personally believe that such encounters are very important.
ということでですね、全く理系と文系で全然違うんですけど、そういう人たちが出会い話し合うことによってお互い影響していくということだと思いますし、また池田菊成先生はその後ですね、味の素今の旨味成分を発見していくということになりますので、出会いっていうのは非常に大事なんだなというふうに思っている次第でございます。
Since I became professor of my current lab, we've been conducting research with the aim of developing something useful for society, centering on monozukuri, which means manufacturing, in consideration of the fact that Professor Ikeda was the first-generation professor of our lab. I apologize for this roughly illustrated explanation, but we have been conducting research on cyanide-bridged metal complexes. Titanium oxide and iron oxide, etc., to create materials with novel functions. I would like to introduce some of these materials today. First, I will introduce you to the lambda type, as shown in the middle here, the one called lambda TI305. You may have heard the term unused heat. Currently, we burn various energy resources to generate electricity. But 38% of the energy from these resources is discharged from factories and power plants as unused heat, which has not been utilized. Of that unused heat, 78% is below 200 degrees Celsius, so it is wasted. When the temperature of waste heat is high, such as above 500 degrees Celsius, it can be used with thermoelectric conversion materials. However, when the temperature is below 200 degrees Celsius, the waste heat cannot be utilized and is currently discarded, being discharged entirely into the atmosphere or seawater. Thus, it is desirable to develop materials compatible with medium and low temperatures. To store heat, a heat storage material is needed. As heat storage materials, sensible heat materials, such as bricks or concrete, are usually used. Latent materials, such as water, as the most representative example, are also used. These materials store heat associated with the solid-liquid phase transition. In any case, the stored energy is usually released spontaneously over time. In layman's terms, they cool down. Therefore, if thermal energy can be stored for a prolonged period of time and retrieved on demand, it can be effectively used as renewable energy. However, this is not actually possible. In the world of heat storage materials, it is known as a blue rose, with the common understanding that heat cannot be stored. If heat can be stored, then the heat can be reused. Now let me explain about the materials. We have focused on titanium oxides as possible materials. These materials are usually represented by TiO2, Ti4+, which is a white pigment. Most paint for white walls uses this pigment with this type of titanium oxide as a component. In Japan, it is used as a photocatalyst and in face powder. Trivalent titanium oxide has one 3D electron, whereas this type has 0 3D electrons. This one has 1. Sorry, this is understandable only for those who major in science. Anyway, this type of titanium oxide is a black pigment. It is used as a heat absorber and as a pigment for eyeshadow. Using these materials, we've been exploring nanoparticulation, in particular of this one. When we nanoparticulated this black one, we came up with a new crystal structure that had never been reported before. We named it lambda trititanium pentoxide. Now let's look into what its properties are. We created this substance by confining titanium dioxide in silica matrix and heating it to 1300 degrees Celsius while keeping it small so that it did not grow to a larger size. This crystal structure was thus born. We used this fabrication process to prepare particles with certain larger sizes and, in this case, obtained a 200 nanometer by 30 nanometers stripe-like crystal. We then identified this size as the maximum particle size we can obtain with this crystal structure. We also found that this is a new material and that it comes in many different forms and morphologies. Interestingly, when we applied pressure to this material for molding, because the powder form is inconvenient for practical use, by changing the pressure slightly, our original lambda titanium pentoxide underwent a phase transition to beta-type titanium oxide, which is a known structure. The crystal structure of ordinary trititanium pentoxide is generally the beta phase. We found that pressure induced a phase transition of our original material, resulting in a beta phase material. In this graph, the phase fraction is shown on the vertical axis, and you can see that, when pressure was applied to the lambda phase, it became beta phase. The pressure at which this pressure-induced phase transition occurred was 60 megapascals. 60 megapascals is 600 atmospheres, which may seem insignificant to some of you. However, the pressure used to induce a phase transition of ordinary titanium oxides from rutile to brookite is 20 gigapascals. Mega and giga are 10 to the 6th and 10 to the 9th, respectively. Thus, a pressure of 20 gigapascals is 3 orders of magnitude higher than a pressure of 60 megapascals. In addition, these materials are ceramics, which are generally said to be hard, but our new material is unique because it undergoes a phase transition at a lower pressure of 60 megapascals. This pressure is somewhat higher than that at the tip of a stiletto heel, which is 10 to 12 megapascals. We also examined the amount of heat produced during this phase transition. Here, when pressure was applied to the lambda phase, the amount of heat emitted was 240 kilojoules per liter. In the case of the latent heat storage materials I mentioned earlier, the amount of heat emitted was 320 kilojoules per liter for the solid-liquid phase transition of water and ice, 165 kilojoules per liter for that of ethylene glycol, and 140 kilojoules per liter for that of paraffin. Thus, our material is at the same level as these. Furthermore, our material produces such an amount of heat with a solid-to-solid lambda to beta phase transition. When a solid-to-liquid transition occurs, the liquid requires containment or other measures to be handled, which makes it very difficult to use in practice. However, because our material undergoes a solid-solid phase transition, such handling-related problems do not occur. In addition, it releases a large amount of heat. We also found that the beta phase obtained by this pressurization returns to the lambda phase when it is heated. The phase transition from beta to lambda occurs at around 190 degrees Celsius. This graph has enthalpy on the vertical axis. Please think of this as energy. The horizontal axis represents temperature. As shown here, the pressure-produced beta phase becomes the lambda phase at 190 degrees Celsius. If this graph represents ice and water, for example, the ice becomes water at this point. However, in the case of water, it turns back to ice at this temperature. By contrast, our material exhibits different behavior. Once this material becomes the lambda phase, it remains in the lambda phase for an unlimited time, even if the temperature is raised or lowered. However, it releases heat only when pressure is applied. Thus, it turns out that our material can store latent heat. We also describe our material as being like a blue brick that can store heat over a long period of time because its color is a bit bluish and its composition is like that of a brick. We think of it as a blue brick, not a blue rose, and that's how we perceive this material. This is a video explaining its mechanism.
The mechanism of pressure-induced phase transition is explained using the thermodynamic model. Gibbs free energy versus lambda phase fraction curves are shown with lambda phase on the right and beta phase on the left. Lambda phase, shown with blue balls, is maintained at all temperatures due to the energy barrier between the two phases. Here, we focus on the Gibbs free energy curve at 300 Kelvin and take a look at the effect of external pressure. By the application of pressure, the Gibbs free energy curve gradually changes, and at 60 megapascal, the energy barrier disappears, causing the phase transition from lambda to beta phase, shown with the red ball. When the pressure is released, the energy barrier reappears, but beta phase is maintained since it is energetically stable. Next, the heat storage process and the pressure-induced energy release process is shown. When beta Ti305 is heated, it transforms to lambda Ti305, accumulating the latent heat energy, and the lambda phase is maintained in the cooling process due to the energy barrier in the Gibbs free energy curve. By applying pressure, the energy barrier disappears, and pressure-induced phase transition occurs from lambda to beta phase, releasing the accumulated heat energy.
This video is also available on the Nature Family Journal's website, if you're interested in watching it. Thus, we propose the concept of long-term heat storage ceramics. This concept is currently being studied in a national project. We're attempting to control these materials from various points of view. For example, these materials instantaneously produce heat when you tap them. We did not know until we tried this experiment that one of the most desired performance characteristics of thermal storage materials is staggered heat generation and utilization times, as I mentioned earlier. However, I hear that there is also a need for materials that can produce heat instantaneously. This material already meets these needs. In a joint research project with a company, we found that when a portion of lambda trititanium pentoxide is replaced with scandium, though I mentioned earlier that this material absorbs heat at 196 degrees Celsius, we lower this temperature to about 67 degrees Celsius. This temperature is lower than the boiling point of water, so it's very useful. We still have a number of challenges to address, but we are getting closer to being able to control heat storage temperature. When we have heat storage materials that function at a temperature below 100 degrees Celsius, we will be able to use the materials in various facilities related to power plants. We've also been featured in a lot of media coverage. This was amid the COVID-19 pandemic, so I was wearing a mask. We're also substituting magnesium for scandium because scandium may be a little more difficult for practical application. This research is being conducted in collaboration with the Denso Corporation. We are also looking into possible applications for these materials. The reason we started this research in the first place was because of its usefulness for solar thermal power generation systems. In Japan, solar photovoltaic generation is the mainstream, but in Europe, where the climate is dry with long hours of sunlight, solar thermal power generation is mainly used, although it is relatively simple. The way solar thermal power generation works is that mirrors are used to collect light to heat the oil in an oil pipeline, and the hot oil is then used to turn a turbine. The heat stored in a thermal storage tank during the daytime is then used to run the turbine at night. So what is in this thermal storage tank? The answer is brick. Because the material we developed is a kind of brick and its performance is similar to that of brick, and because it can also store latent heat, we thought it could be used effectively for solar thermal power generation. We therefore began our research on heat storage. Another area of application is in automobile fuel efficiency. We are working with Toyota. Currently, various vehicles, including EVs, are being developed, for which we believe our material will be useful for improving fuel economy. The most important factor in increasing fuel efficiency of a vehicle is the temperature at the time of startup. When a vehicle first starts up from a cold state, the pistons, cylinders, and various oil systems are cold. Therefore, if we can warm these areas, we can improve fuel efficiency very effectively. We are therefore promoting applications in this field. Also, this material itself changes when exposed to light. This is a property that we were the first to discover, and it is research that we carried out before our work in heat storage. We are also studying the optical functionality of the material, which can transition back and forth between the lambda and beta phases, depending on the light conditions. This study was also covered by the media. We are also examining the possible various applications by preparing various prototypes of this material. Because the powder form is difficult to use, we are processing it into various forms. Here are some examples. This is a report from last year, which is not our research. Researchers overseas studied this lambda trititanium pentoxide and reported that it can absorb sunlight with a 96.4% efficiency and change water from liquid to gas. It is easy to see that applying this material to buildings would provide an urban cooling effect. On the other hand, an application was proposed in which this material could be used to absorb heat and evaporate seawater to obtain fresh, potable water in areas where there is no fresh water. To be honest, this idea had never occurred to me, but as such, applications of this material are expanding. As the person who first discovered the material, I find it very interesting that its applications are expanding, and am very happy to see it.
正直私としては全くこれはちょっと思い浮かばなかったんですけれども、そういった応用も今広がってきているということで、最初に材料を見つけて、そういった応用が広がっていくというのは大変興味深いなというふうに思っていますし、ものを作った人間としては嬉しいところでございます。はい。Lambda TSL5 のを見つけた。
I have talked about lambda trititanium pentoxide from its discovery to its application. The details have been reported in Nature, so I would appreciate you taking a look at the article if you're interested. Let's move on to the next topic. I will give you a quick overview of the investigated materials and then show a video on how to make them. Among several materials, I will first talk about metal complexes, which are combinations of metal ions and organic materials. We are working to design various magnets, basically focusing on magnetic properties, especially on ferromagnetism, using these metal complexes.
そういったものを使って基本的には磁石、強磁性に注目しながらいろいろな磁石を設計するということをしてきております。
Here is one example of what we synthesized. You can see metal ions and organic heterocycles, or benzene rings. You see the positive and negative here, but this is a unit cell, so please think of it as a crystal structure that has grown infinitely large. When these crystals are prepared, left and right-handed structures are separately formed, with plus and minus structures, respectively. Furthermore, it is a magnet. We've created a material that is a magnet and also has this kind of chiral structure. As an application of this material, we demonstrated this. When 473 nanometer blue light is irradiated onto this material, it becomes a magnet and the polarization plane becomes horizontal. When red light with a differing wavelength is used, the characteristics of the magnet change such that the output vertical secondary harmonic light is emitted at a 90-degree angle. The output light is called second harmonic light, and now we could control it by irradiation for the first time. As for its applications, it may be easier to understand if we refer to it as a storage medium like MO disks, which were used in Japan a long time ago. These disks basically use the polarization plane of light for detection. This is one of the possible applications of this material. This material was also featured on the cover of the journal. I'm not sure if the members are the same as current ones. Oh, they are still working in my lab. They're also members of my office. I would be happy if you would communicate and support them going forward. Normally, you might not think of a magnet as reacting to water vapor. However, 20 years ago, I was thinking about what kind of material would serve as a magnet that changes its performance in response to water vapor, or humidity. Then, I actually found this material. It is written as cobalt chromium, CN6, called Prussian blue analog. As you can see, the color changes depending on the humidity. We call them cobalt pink and cobalt blue. The number of water molecules coordinated around the pink cobalt and that coordinated around the blue cobalt are different, and the amount of contained water differs depending on the humidity, thus resulting in different colors and magnetic properties. This figure may be a little difficult to see. The vertical axis represents magnetization, and the horizontal axis represents temperature. The magnetic phase transition temperature changes like this, an example of how it can be reversibly changed. This is the first example of a humidity-induced magnet, and we have been advancing further studies on it. This is our recent result. In this curve, the vertical axis is the ionic conductivity. This material shows a change in ionic conductivity when exposed to light. Ionic conductors are commonly used as battery materials. We wondered if it would be possible to switch ion conductivity with light, and we actually succeeded in switching it. It's a little difficult to explain the mechanism with just this material, but we've been trying to create something that has never existed before by using complexes. I would now like to talk about our most recent result, which is one of the main topics of today's presentation. It is the development of pressure-induced cooling solid materials. Currently, energy used for air conditioners and refrigerators accounts for as much as 20% of our electricity consumption. I mean, we use as much as 20% of electricity for cooling, for which we generally use gaseous cooling agents. We often use refrigerants that undergo a phase transition between gas and liquid, but there is a need for an alternative refrigerant that undergoes a solid-to-solid phase transition, which will help solve various environmental problems and save energy. Although freon gas, a chlorofluorocarbon, is no longer used, which has reduced the destruction of the ozone layer to a great extent, there is no need to worry about such an adverse environmental impact when we use a solid refrigerant. You may have noticed that computers, for example, use a lot of electricity, generating a lot of heat. Thus, it is often said that air conditioning must be strengthened. This is why solid refrigerants are attracting increasing attention. In response to this situation, we've created a new Prussian blue analog based on rubidium, manganese, iron, and cobalt. All of these complexes I have mentioned are members of the Prussian blue family. We've been studying this material. As for solid refrigerants, we've been looking into possible solid refrigerants that are controlled by pressure. When you apply pressure this way, and the phase transition temperature shifts, if you release the pressure, it will shift backwards. Now we see the high temperature phase on this side and the low temperature phase on this side. The high temperature phase is in a higher energy state. This one is in a lower energy state. To explain once more, at 300 degrees Kelvin, if a material exhibits this kind of thermal hysteresis, or thermal phase transition, it is in a high phase temperature at 300 degrees Kelvin and in this kind of energy state. However, when pressure is applied, for example, the material shifts to this side. Because of this applied pressure, it will shift from a high to a low temperature phase, a low energy state, and will release heat to the surroundings. Then, when the pressure is released from the material with accumulated heat, the material enters a high temperature phase, namely a high energy state, which means that it absorbs energy from its surroundings. By using this principle, we are attempting to design a phase transition material to achieve a cooling effect. The explanation of this picture is a little difficult, but the cooling effect due to pressure is called the barocaloric effect. You don't need to memorize the term. Anyway, it refers to using pressure to cause a phase transition. What you see in this figure is that here, which says 0.1 megapascals, is 1 atm, and when more pressure is applied, it moves to here, 560 megapascals. In the figure, it's here. I'm afraid this explanation might not work for you. What I'm trying to say is that the pressure increases from 0.1 megapascals all the way to here. And when it reaches 560 megapascals, for example, it becomes this state with a temperature of 88 degrees Celsius. The moment this applied pressure is released, the temperature quickly drops by 85 degrees Kelvin. This is a theoretical value based on experiments. We refer to this temperature as the adiabatic cooling temperature, and this was the highest adiabatic cooling temperature achieved among various materials studied in the world. In other words, we have found the best cooling material in the world. We then plan to measure the actual adiabatic cooling temperature. This is a video showing the mechanism. It's not easy to understand by verbal explanation, so we've made a video. This is around 300 Kelvin, and the vertical axis shows the entropy. So this is 1 atm, or 0.1 megapascals. This is the material to which a pressure is applied from above. For example, at 38 degrees Celsius, when the material shifts from the high temperature phase to the low temperature phase like this, it releases heat, dumping the heat downward. When the pressure returns momentarily from this state, it returns to the high temperature phase, so it cools itself tremendously. The magnitude of the cooling effect is, although this is based completely on theoretical calculations, 59 degrees Celsius. Thus we confirmed with calculations that this material can lower temperature. This result means that we've developed a material that repeatedly produces heat when pressure is applied instantaneously, and decreases in temperature when the pressure is released instantaneously. this is a field that has just started developing and is attracting a lot of attention. In fact, we fought with a journal reviewer about the paper. We were told that, if it was so great, we should actually measure it. So we decided to do so, and because there is no device in the world that can actually measure this, we made our own device through trial and error. It is extremely simple. We simply inserted a thermocouple, a kind of temperature sensor, into the molded material. The temperature of the material increased by 44 Kelvin when pressure was applied instantaneously, and decreased by 31 Kelvin the moment the pressure was made constant and then released. This is, even written as roughly as this, something no one had ever seen before. This material also achieved a world record. So the 85 Kelvin temperature change I mentioned earlier is roughly what this should be theoretically. However, because the measurement was made with a device with such a simple structure, the measured temperature change was only about half of what it should have been. We would like to further refine this to produce results closer to the calculated adiabatic cooling temperature, as mentioned earlier.
だからさっき言った85ケルビンってのは大体これが85ケルビン理論値的には85ケルビンになるはずなんだけど、装置の今みたいな装置なんでなんか半分ぐらいしかなんかこうなんか下がらなかったっていうのがそれは答えなんで、ちょっとこれ工夫して先ほどの断熱冷却温度に近いものにしていきたいと思ってます。でこれ繰り返しはどうなのって話で。
We then examined the performance of the device when measured repeatedly, and it amazingly maintained the same performance even after 100 repetitions, with no degradation in performance. I was also surprised at the reproducibility of this material. However, if it is actually used as a solid refrigerant for real fridges, it is required to maintain its performance after 10,000 repetitions or so. I therefore think this aspect will require further study going forward. In any case, as a phenomenological matter, we've observed the largest levels of cooling capacity and pressure-induced properties to date. We are currently conducting research with the Eisen Corporation, an automobile parts manufacturer. This will be the last topic for today. I don't want to overstay my welcome, so I would like to end by talking a little bit about epsilon iron oxide. We discovered and have been studying epsilon iron oxide since 2004, and I would like to talk about the various possibilities of this material. So iron oxide, just simple iron oxide. The question is, how was this material found in the first place? Usually, Fe2O3 is either in the gamma or alpha phase. The one that everyone is most familiar with is alpha phase. It is red rust, or is used as a red pigment. We've also made titanium oxide in the form of nanoparticles, as I explained earlier. For Fe2O3, we also suppress the growth of nanoparticles larger than about 20 nanometers, which is very small, by trapping them in a glass. This fabrication method produced a material that exists not as the gamma or alpha phase, but as epsilon iron oxide. This material is characterized by its extremely large coercive field of 25 kilo-Ørsted, and when iron is partially substituted by other metals, the coercive force field becomes even stronger. Having a large coercive field means it can be made into smaller magnets. For example, this is about 8 nanometers in size, but its coercive field reaches a value of about 5 kilo-Ørsted. Common storage media have a coercive force of about 3 kilo-Ørsted. By the way, the PIP Elekiban that you put on your stiff shoulder has a magnetic flux density of about 1.5 kilo-Ørsted, although it had actually been expressed in Gauss in the market. It has been found that this epsilon iron oxide can constitute a single-order nanometer-sized magnet that does not lose its magnetic performance even at sizes less than 10 nanometers at the smallest. One of the applications is this kind of magnetic recording tape material. We are making a prototype that could be used for such applications, although it is not limited to tapes. A storage device was designed as shown here. It provides a very sharp signal response, and this is what it looked like. This is a non-magnetic layer, and this is the recording layer. The magnetic tape, which you don't usually see as a recording medium, is attracting a lot of attention as an archival medium for big data. This is intended for what is called cold data to be used once or twice a year. However, it is currently necessary to record a huge amount of data, so this can be an application of epsilon iron oxides. Another application is now being studied because this material absorbs radio waves, especially millimeter waves in the 30 to 300 gigahertz range, so it can be used for various radio communications, vehicle radar, human body scanners, broadcast radio communications, communications between mobile phone base stations, and ADAS, Advanced Driver Assistance Systems. These applications use frequencies such as 60, 76, 94, 120, and 140, and adjusting the frequency of this material to match these eligible electromagnetic waves to be absorbed. We've been working with various companies to create products using these materials. In acknowledgement of such a discovery, we were invited to exhibit our material at the Science Museum in London, UK. This was a special exhibition on big data and security in the Internet of Things society, and our material was displayed. On this occasion, among other exhibitors, including Twitter, the University of Cambridge exhibited quantum cryptography technology, and we exhibited this material. Our material was exhibited at the National Museum because our materials are attracting attention as next-generation recording materials and also as millimeter wave absorbing materials. This material is now being commercialized by various companies, so if you're interested, you can acquire it. Iwatani Corporation, Tokyo Oka Kogyo Co., and here is Panasonic. Thin films like this can be produced and are available. I would like to summarize at the end. Considering the fact that epsilon iron oxide is the smallest hard ferrite magnet, and that it absorbs millimeter waves, as I have mentioned, we've been studying a new type of focused millimeter wave assisted magnetic recording media. Our aim here is to make the recording media smaller and smaller. However, as we make the particles smaller, the magnetization becomes unstable, so we have to increase the anisotropy to stabilize the magnetization. Increasing the anisotropy will cause problems such as the inability to write data. This is what is called a trilemma. To solve this problem, we are now proposing using this recording material assisted by the ability to absorb millimeter waves. This is a joint research project with Fujifilm Corporation.
それを解決する方法として、この記録材料とあとはミリ波を吸収させてアシストするっていう方法がないかっていうような提案を今しているということでございます。これは富士フィルムさんとやっているということです。ちょっとね、細かい内容ですので、ここではその
I won't go into the details here, but we are working toward the possibility of recording by combining both magnetic fields and millimeter waves to record data, which has attracted a lot of attention and has been reported in The Economist and other publications. Lastly, the epsilon iron oxide, which I noticed from the beginning when I handled it, is light in color. Normally, magnetic materials are dark in color, they are blackish. However, this material has the characteristic of being very light in color. Because of this light color, I had in my mind the possibility of using it as a pigment or dye. In the meantime, it has recently been discovered that the surface of ancient Chinese ceramics was actually glazed using epsilon iron oxide, which means that ancient ceramics, especially those known as Tenmoku tea bowls from the Southern Song dynasty, were white, black, or brown with various colors. They were known to have various colors, such as black, brown, or in some cases purple, like this one, but it remained very mysterious that these colors could not be reproduced with modern technology. We only knew that iron ions existed on the T-ball's surfaces. Normally, cadmium is used as a pigment, but it was clarified that there was no such pigment and that there was only iron on Tenmoku bowls, but we did not know how such colors could be produced. It was finally clarified that the colors were those of epsilon iron oxides. They are structural colors. This is the reason why the bowls appear in various shapes with different structural colors. Incidentally, Tenmoku tea bowls were made in the Tenmoku region of China, and among bowls produced in this region, those with black color were considered an abomination and were thrown away. However, 4 of them came to Japan, and one of those 4 is shown here, the Yohen Tenmoku tea bowl, which is designated as a national treasure in Japan. Originally, there were 4 of them. One of them, the Yohen Tenmoku tea bowl that was said to be exceptional and owned by Nobunaga Oda, was lost in the Honnoji incident. The remaining 3 are shown here. Of course, I cannot analyze these national treasure bowls, so I do not know if it is really epsilon iron oxide or not. But this Tenmoku tea bowl has become quite a topic of conversation in China, since it was discovered that the surface of the Tenmoku tea bowl and other ancient Chinese bowls were actually glazed with epsilon iron oxide. Then, what are structural colors? First, the colors are from oxides. The colors of swallowtail butterflies are light, and the components themselves are transparent. The colors we see are structural colors. That is, they are the colors of the structure, like the color of soap bubbles. Normally, when iron oxides are in the gamma or alpha phase, they exhibit strong colors. Thus, even if we add them to some structures, they do not represent structural colors because the pigment never gets lighter in color. We can therefore say that the light color is a unique characteristic of epsilon iron oxide. Last November, there was a grand special exhibition and symposium at the Palace Museum in the Forbidden City, and I was invited to give a lecture at the special exhibition of the Tenmoku tea bowls. I was invited to give a lecture. This is the lecture I gave at the Forbidden City.
ちなみにこれ通常のですねなんですかねまあいいですあんまり言ってもしょうがないですけどまあ試験場での講演をしてきたということでございました。
Lastly, I don't have to show you this, but this is a list of our patents, not our papers. JP represents Japan, CN for China, and EP for Europe. Thus, along with writing papers, I am writing and filing patents in Japan and abroad.
ということで、特許をこういう形で、論文を書くとともに特許を書いていくというようなことをしております。日本と海外。
This is the end of the list. As you have seen, I have already been issued about 300 patents.
300ぐらい特許出しているということでございまして。
Now I would like to conclude my presentation by saying that it all started with curiosity, basic research, and encounters. In the case of Professor Ikeda, that was an encounter with Mr. Sosuke Natsume which inspired him so much. But in my case, I had the opportunity to meet people from various companies and businesses, and I had chances to talk with a vast number of people, which inspired me in many ways and gave me deep insight into many things. From there, I have developed basic research to applied research, and I humbly wonder if we are making some contribution to society, at least partially, or if we are in the process of doing so. I'm often asked which is more important, basic research or applied research, or how they are connected. It is difficult for me to answer this question, but from my perspective, that is how they are connected. So although basic researchers may be more on the portion on the left side here, and applied researchers may be more on this side, I think that a great contribution to society starts with great curiosity. Please note that this is a single example of mine. I am sure there are many people who have different perspectives and ways of thinking. But based on my experience, if there is anything that I can tell you, it is that I would like you to cherish your curiosity and encounters in ways I shared with you today. Thank you very much, Professor Okoshi.